Hypothalamus Artificial Intelligence, HY. It presents its vision of the new artificial intelligence, based on artificial business management, artificial business brains, and enterprise-wide optimization systems. A new way of looking at artificial intelligence, which will change the world as we know it. Lecture prepared by Engineer Jesus Velasquez Bermudez, Chief Scientific Officer of Hypothalamus Artificial Intelligence. Jesus has been awarded by the Industrial Engineering and Operation Management Society, IEM, for his research work on artificial intelligence applications in businesses, industries and services. HY's research capitalizes on the evolution of artificial intelligence to decision-making artificial intelligence. Artificial intelligence focuses on and sustains the study of biological neuron networks to mimic pattern recognition, and today it is identified with copilots, agents, and in general advisors, such as ChatGPT, who help human beings recognize patterns and execute the basic processing that with such information, this translates into the automation of the basic intellectual activities of the human being, for example, the production of a report, or identify one image among millions on the fly, etc. Artificial intelligence focuses on and sustains the study of biological neuron networks to mimic pattern recognition, and today it is identified with copilots, agents, and in general advisors, such as ChatGPT, who help human beings recognize patterns and execute the basic processing that with such information, this translates into the automation of the basic intellectual activities of the human being, for example, the production of a report, or identify one image among millions on the fly, etc. The fundamental gain for humanity is that the difference between decisions based on simple mental models, compared to decisions based on formal mathematical models, yields superior performance on the order of 15 to 20%. It could be said that artificial intelligence for decision-making is the goose that lays the golden eggs of humanity, not only to increase economic wealth, but to achieve a world that consumes much less energy, and thus perhaps solve the problem of global warming. The globalization of this type of artificial intelligence would avoid making bad decisions, eliminating all the problems that this entails. Artificial business management. Artificial intelligence robot Mika is the leader of the luxury liquor company, Dictator, based in Poland. Dictator has signed a contract with Mika, who now sits on its board of directors and holds the position of CEO. Enterprise-wide optimization will be the methodological approach of the artificial hypothalamus of the cognitive robots that run companies. That is the future that awaits us. This lecture presents the process followed by HY, to build artificial intelligence systems for decision-making, for the artificial management of companies. The vision presented is not only theoretical, but also based on the praxis of more than 50 years solving decision-making problems, whose methodology evolved to reach artificial brains, and the technology to enterprise-wide optimization systems. HY hopes you enjoy the conference. Artificial brains, integration of artificial intelligence and mathematical programming, are the result of HY's research in disruptive mathematical modeling methodologies for Industry 4.0. And they are the basis of the computational architecture of the enterprise-wide optimization systems. For more information, those interested are invited to watch the video. Artificial brains, artificial intelligence and mathematical programming integration. From human brains to artificial brains. Velasquez, in 2021, published on SSRN, the paper Artificial Hypothalamus, Artificial Intelligence and Mathematical Programming Integration, in which the foundations of artificial brains, and more specifically of the hypothalamus, are laid. The article, and others later, carefully studies the relationships between the structures of the neocortex, with those formed when a mathematical problem is atomized, to use large-scale optimization methodologies, oriented to the partitioning and decomposition of systems, and they define the artificial brain in semi-detail. This is a disruptive vision of artificial intelligence, considering the power of computers, the evolution of mathematics, and the Internet of Things. This conference explains in a summarized way this evolution, based on the current state of AI. A complementary document is Artificial Brains, Augmented Artificial Intelligence, Artificial neocortex plus artificial hypothalamus plus artificial hippocampus. Human intelligence has evolved along with human beings. To understand this process, HY describes human intelligence as composed of three intelligences: mental intelligence, mathematical intelligence, and creative intelligence. Mental intelligence is the intelligence with which humanity began to develop, starting with Homo sapiens. The next level of intelligence is creative, or analytical, which is what allows us to make new discoveries that will be fundamental for the development of humanity. Creative intelligence is fundamental to the development of mathematical intelligence, which builds mathematical models based on the knowledge developed by creative humans. Mental intelligence underpins the mental models that every human being requires to start making their decisions. Human knowledge is supported by three types of intelligences. Mental intelligence: it is the abstraction or conception of what is perceived by individuals about a given issue or problem. Mental models are constructed with the knowledge, experiences, assumptions, perceptions, intuitions, informal inductions, deductions, and values of the individual. They are elementary models that are not exposed in public and therefore have a validity limited to the individual. They have their origin in the evolution of the human being, hominization, from the most primitive ancestors, Australopithecus, to the appearance of our species as we know it today, Homo sapiens. All human beings manage mental models, very quick to solve, and, in their absence, easily copy themselves from a more influential individual, and more recently, are implanted in human beings through the ochlocracy of mental models distributed by social networks. When intelligence works under this model, we will call it mental intelligence, which exists and develops in all humans. Mental intelligence and pattern recognition. Mental model is oriented to identify patterns, its foundations are not mathematical, and respond to data processing, and evaluation of eventual, and systematic, experiences. It is based on good practices. Pattern recognition is a data analysis method that uses machine artificial intelligence algorithms to automatically recognize patterns and regularities in data. This data can be anything from text and images to sounds, or other definable qualities. Pattern recognition systems can recognize familiar patterns quickly and accurately. Pattern recognition is the activity that most performs the human being, for example, identifies images of people, foods, hydroclimatic conditions, traffic conditions, texts, sounds, and etc. All this with the aim of establishing the conditions of the environment, in the past, the present, and the future, and based on this knowledge make decisions. How the brain identifies patterns is not properly known, but it is mimicked by traditional artificial intelligence. Then, the starting point of the name of artificial intelligence is associated to the pattern recognition. Today, the association is direct, and it seems that artificial intelligence is reduced to this function of the human brain, what has concentrated great amount of scientific research in working in this direction, forgetting other human brain functions. It seems that artificial intelligence is reduced to the emulation of mental intelligence, whose function is little known and explained. That is why it is known by scientists that neural networks can predict how a system will behave, but that in general the parameters found cannot be explained, they have no clear content, just as the humans cannot explain how this function works in the human brain. But this approach cannot be said to have been unsuccessful, as it effectively and massively replaces activities that ordinary humans did not think machines could perform. At first, neural networks were aimed at finding ways of connectivity of artificial neurons, seeking to improve the results of prediction. Something like a statistical model in which many algebraic models are tested, until a good solution is found. Little has evolved to try to explain content in this connectivity. This is the case with GPT. Pattern recognition is a basic human skill, for which we have no explanation. The essence of the so-called artificial intelligence is mental intelligence represented from the study of biological neurons, to emulate and surpass human pattern recognition. In 1943, Warren McCulloch and Walter Pitts created the concept of artificial neural networks. They published the paper, a logical calculus of the ideas immanent in nervous activity. McCulloch and Pitts tried to understand how the brain could produce highly complex patterns, by using many basic cells that are connected. They designed their system based on as they believed our brains work, and patterned it after the biological model of how neurons work with each other. The neural networks were growing, and in practice they took the name of artificial intelligence, displacing other methodologies and technologies that also generate artificial intelligence in the machines. As the diagram presents it, a neural network is an interconnected group of nodes that allows computers to recognize patterns in data. This area of science corresponds to predictive analytics. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets, specialized in performing specific pattern recognition. For this, the basic patterns of ANNs are modified. Convolutional artificial neural nets. They correspond to ANNs specialized in identifying certain types of patterns, such as images. The image presents an example of an ANN oriented to recognize images of numbers written freehand. The result is a discrete indicator associated to the number read. Artificial neural network modeling has evolved to the point where networks with specialized structures can perform specialized functions. GPT is the state-of-the-art of the standard artificial intelligence. Generative Pre-trained Transformers, GPT, are a family of neural network models that uses the transformer architecture and is a key advancement in artificial intelligence, powering generative AI applications such as ChatGPT. GPT models give applications the ability to create human-like text and content, images, music, and more, and answer questions conversationally. Organizations across industries are using GPT models and generative AI for conda, text digesting, content generation, and search bots. ChatGPT, produced by OpenAI, is the state-of-the-art commercial artificial intelligence GPT. Is ChatGPT a neural network? Yes, it is. ChatGPT is a natural language processing model that uses a neural network to power its understanding and conversational responses to users' text prompts. Specifically, ChatGPT works with a large language model, LLM, called GPT-3, developed by OpenAI and which has 175,000 million parameters. This is due to the current computational power and the great availability of data on the web. ChatGPT uses a feed-forward neural network as well as a normalization layer to generate its human-like responses. The feed-forward neural network applies a nonlinear transformation to the input stream, ensuring that the model can learn complex patterns in each dataset. The normalization layer stabilizes this training process by making sure that the input values have a relative scale size. It uses a machine learning technique, called fine-tuning, to ensure it responds to prompts accurately. However, it should be noted that, like any predictive method, it meets certain basic characteristics. You can set the accuracy of what you predict for the sample. In a regression process, this precision is called R-squared. As the number of parameters increases, the accuracy increases. But too many parameters lead to problems of overestimation. Accuracy depends on the quality of the sample, it can never explain what is not in the sample. But its ability to solve real decision-making problems, unlike advanced pattern recognition, is minimal, if not non-existent. Specifically, to solve a question such as, how much should I produce from the different SKUs in each of the plants in a supply chain? For many data scientists, data-driven models are the only artificial intelligence out there. This includes academic teaching. This leads to a problem in the development of artificial intelligence, as many executives and managers who are not experts in AI think that the only artificial intelligence that exists is predictive. Therefore, it is applications like ChatGPT, and the like, that most consider the AI of the future. HY disagrees with that assessment. Mathematical intelligence underpins the mathematical models that some humans develop to make their decisions. Second, mathematical model is a scientific representation which make use of mathematical language to describe or to explain the portion of reality that is of particular interest to an individual. It is the result of the research carried out by certain humans. The mathematical models are growing as analytical tools that provide greater processing speed to the investigation. For its understanding requires formal training in mathematics and in the science being modeled. These models increase the intelligence of human beings, creating large differences, chasms, between them. When intelligence works under this model, we will call it mathematical intelligence. This ability to understand mathematics, and to handle it, does not extend to all humans. It is necessary to acquire knowledge and experience, to handle this intelligence properly. At present, its development is directly related to the ability to handle computational and mathematical technologies. Mathematical intelligence and decision-making. Decision-making process is the final objective of any person or organization, which seeks to make the best decisions from its point of view, its criterion. This process, when carried out in real time, requires a great capacity for mathematical calculation, to handle the complexity of the real world, which increases over time, since the universe increases its entropy at each moment. When humanity began its evolution, it only had mental models to support its decisions, which seriously limited the speed of the evolution of the species, due to the little, almost zero, capacity of mental models, which led the human being to make decisions with very few calculations, or without them. Thanks to analytical intelligence, human beings develop their mathematical intelligence, which has led us to Industry 4.0. Since the creation of AI, and the advent of the computer, it can be said that predictive methodologies displaced prescriptive ones, in what was called artificial intelligence. For the convenience of the reader, decision-making artificial intelligence, DMAI, will be presented in comparison to traditional artificial intelligence. The first big difference is that DMAI is based on the study of mathematical intelligence, which focuses on the representation of the physical world through algebraic formulas, or through differential calculus, and solves problems using exact mathematical algorithms, aimed at finding the best decisions. This area of science corresponds to prescriptive analytics. The displaced methodology is formal mathematical modeling using algebraic equations, and/or differential equations. This is related to the use of mathematical programming, or optimization, to support decision-making. It is easy to show that in most companies, mathematical programming is not considered to produce knowledge, like the human. This is because decision-making does not concern researchers who promote artificial intelligence. Practitioners, perhaps fanatics, of traditional AI, have classified mathematical programming algorithms as the exact methods, not with the intention of highlighting them, and promoting their learning. On the contrary, they disqualify them because in theory they cannot be used. But this is false. The essence of mathematical intelligence modeling is based on the study of the human brain, based on neuroscientific studies. The result is the production of artificial brains. The creator of the human brain conceived it as the integration of three main organs, or systems: neocortex, hypothalamus and hippocampus. The hypothalamus is part of the thalamus. The artificial brains corresponds to the scientific foundations, more specifically mathematical fundamentals, that allow to connect multiple mathematical models, algorithms or robots, exchanging information between them to obtain a common goal, and act as holistic intelligence of the organizations, or parts therein. Like the human brain, the artificial brain is composed of the following artificial components: neocortex, hypothalamus, and hippocampus. The hypothalamus is the organ that ensures the proper functioning of the human being. The connectivity of neurons in the cortex determines how the hypothalamus should function. The hippocampus is responsible for managing memory, which interacts with the hypothalamus, to determine the actions that the human being will perform, that is, decisions. Artificial entrepreneurial brains are based on these hypotheses. The neocortex contains millions of neurons that communicate with each other, to capture the world that occurs around the human being. The connectivity of these neurons does not occur based on a dense network that connects all neurons to each other. Connectivity is based on a sparse network, which can be assimilated to a sparse array. Neuroscientific studies associate the network of neurons of the cerebral cortex in layers, and in columns, connected in an organized hierarchical way. In mathematical models, it is common to use a matrix that relates columns with variables, and equations with rows. The normal thing is that these matrices are sparse, structurally similar to that of the human cortex. This section is based on the paper "Why Does the Neocortex Have Layers and Columns? A Theory of Learning the 3D Structure of the World." Neocortical regions are composed of columns and layers that performs robust object learning and recognition. Columns integrate their changing inputs over time to learn complete models of observed objects. Lateral connections across columns allow the network to more rapidly infer objects, based on the partial knowledge of adjacent columns. Because columns integrate input over time and space, the network learns models of complex objects that extend well beyond the receptive field of individual cells. The image presents the hierarchical distribution of neurons in the neocortex, joining brain, neocortical columns, simple neurons and ion channels. This is the starting point of the Hawkins model. Hawkins proposes the concept of regions, groups of cells organized hierarchically, interconnected, but with a low density of links, sparse. This is the fundamental representation of the 3D connectivity of neurons in the neocortex. This structure has the same characteristics as those generated when a monolithic model is divided and decomposed into an atomized model, to process it in parallel. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. This diagram shows a three-level structure. Result of partitioning and decomposition of a system, using a simple methodology of large-scale optimization, like Bender's theory or Lagrangian relaxation. Based on the concepts of partitioning and decomposition, it is possible to decouple a system, to obtain vertical structures partially similar like of the human neocortex. Cross-decomposition, developed by Van Roy, makes it possible to establish complex optimization processes, in which multiple methodologies are used on a large scale. This allows the problems to be adjusted to the most convenient methodology for the solution of each subproblem. This implies a universal conversation between multiple algorithms, built with different methodologies. It also frees the decomposed problem from bidimensional hierarchical tree-like structures, enabling horizontal communications between subproblems. From the point of view of multi-layer structures, cross-decomposition results in the exchange of information between multiple layers, of different columns, like the actual structure of the human neocortex. As in the human cortex, lateral connections between columns allow the network to solve problems more quickly, based on partial knowledge of adjacent columns. The hypothalamus must coordinate all the processes that the human being carries out. The artificial hypothalamus must connect the multiple mathematical models, algorithms, that are part of the artificial brain, exchanging information between them to obtain a common goal, mathematically an objective function. This activity must be autonomous, permanent, and based on distributed processing. Hippocampus store the experience, and the knowledge acquired over time in the human brain. The learning process of the human being is concretized in memory, which accumulates information to face each new situation using the accumulation of knowledge that has been made up to that moment. This information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. Remember, the operation of the artificial hippocampus is presented as an expert system that must store two types of knowledge: formulation, the components of mathematical models, and historical data of the results generated solving the mathematical problems. Using large-scale optimization methodologies, this information is used as starting point in future uses of mathematical models to support decision-making. The information is stored in the hippocampus where the data is organized according to its age. Like any physical element, its use affects its reliability, and that is why short memory, the one that stores the data of the last days, begins to fail with age, until it is lost, while long-term memory can store very sharp data, but that require greater access time to locate them. Remember, human intelligence has evolved along with human beings. To understand this process, HY describes human intelligence as composed of three intelligences: mental intelligence, mathematical intelligence, and creative intelligence. HY is focused on decision-making artificial intelligence, which corresponds to mathematical intelligence. Within a nervous system, a neuron is an electrically excitable cell that fires electrical signals called action potentials through a neural network. The neuron is the main component of nervous tissue in all animals. Neurons communicate with other cells through synapses, specialized connections that commonly use minute amounts of chemical neurotransmitters, to pass the electrical signal from the presynaptic neuron to the target cell, across the synaptic gap. Neurons are highly specialized for the processing and transmission of cellular signals. Given their diversity of functions performed in different parts of the nervous system, there is a wide variety in their shape, size, and electrochemical properties. For instance, the soma of a neuron can vary from 4 to 100 micrometers in diameter. An artificial neuron is a mathematical function conceived as a model of biological neurons. Artificial neurons are elementary units in an artificial neural network. The artificial neuron receives one or more inputs, representing excitatory postsynaptic potentials and inhibitory postsynaptic potentials at neural dendrites, and sums them to produce an output, or activation, representing a neuron's action potential which is transmitted along its axon. Usually each input is separately weighted, and the sum is passed through a nonlinear function known as an activation function, or transfer function. The transfer functions usually have a sigmoid shape, but they may also take the form of other nonlinear functions, piecewise linear functions, or step functions. They are also often monotonically increasing, continuous, differentiable, and bounded. Transfer functions usually have a sigmoid shape, but they can also take the form of other nonlinear functions, piecewise linear functions, or step functions. They also tend to be monotonically increasing, continuous, differentiable, and bounded. An artificial neural net is based on a collection of connected artificial neurons, which loosely model the neurons of a biological brain. Each connection, like the synapses in a biological brain, can transmit a signal to other neurons. An artificial neuron receives signals, then processes them, and can send to neurons connected to it. The signal at a connection is a real number, and the output of each neuron is computed by some nonlinear function of the sum of its inputs. The connections are called edges. Neurons and edges typically have a weight that adjusts as learning proceeds. The weight increases or decreases the strength of the signal at a connection. Neurons may have a threshold such that a signal is sent only if the aggregate signal crosses the threshold. Defining parameters and topology is a combination of empirical work and scientific work, but there is no mathematical theory that must be respected. The algorithmic process is cyclical, and its convergence is based on the minimization of errors. The precision and representativeness of the process are directly proportional to the number of neurons that can be handled, which is why the development of associated technologies is exponentially enhanced, with the enhancement of computer technologies. HY developed a theory for building networks of artificial neurons specially built to integrate the artificial brain and fit into the structures of the artificial cortex. Starting from the perceptron, the first artificial neuron created, the knowledge of neuronal modeling has evolved, currently having multiple types of artificial neural nets. This new type of neuron will be called mathematical artificial neuron. Its name was derived from the fact that the neuron is built, based on mathematical models that represent a system, and that it does contains logical or intuitive elements. The mathematical artificial neuron is a mathematical model, presumably of optimization, which results from the partitioning and decomposition of a monolithic problem into an atomized model, following the mathematical laws of large-scale mathematical modeling. Two mathematical artificial neurons communicate with each other, forming a network of mathematical artificial neurons. Communication occurs in two directions between the two neurons. The communication protocol between the two neurons is defined by mathematical laws developed to solve atomized problems. The modeler can choose the protocol, but not the communication process, which for optimization is based on the scientific laws of duality theory, and for equilibrium problems in mathematical programming with equilibrium constraints, PEC, methodologies. A mathematical neuron represents a robot, which can communicate with another robot, autonomously, since it knows the mathematical rules that it must respect. This is what happens in the human brain, where autonomic systems communicate with each other to make decisions. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. The mathematical artificial neuron is the technological evolution from the biological neuron, typical of mental intelligence, to the neurons necessary to represent mathematical intelligence, which until now are not produced by the human being. Like all mathematics, theory is cadent, and for those of us who already work in high-complexity mathematical modeling, it is the logical step we must take. It's just widening the look, and thinking a little outside the box. The mathematical artificial neuron is a mathematical superstructure, representing a complete system. A mathematical artificial neuron network can be a neuron of a larger mathematical artificial neuron network. This law of transitivity is typical of large-scale modeling. A large-scale system can be represented by a mathematical artificial neuron, and covers multiple subsystems, where each of them can be represented by a mathematical artificial neuron. Using large-scale methodologies, the mathematical artificial neuron can be divided into two, or more, mathematical artificial neurons, forming a mathematical network of artificial neurons. This process can be repeated, until the smallest mathematical artificial neurons, the atoms of the system, are obtained. The development of artificial intelligence for decision-making at HY is based on the praxis of intensive prescriptive analytics. HY developed OptX, Optimization Expert System, a multi-model optimization artificial intelligence tool, which complies with the principles of an artificial hypothalamus, and the development of methodologies that can be coupled to multi-level mathematical structures, such as those of the artificial cortex, and source code generation, to eliminate manual computer programming tasks. Algorithms swarm. If large-scale multi-level optimization methodologies, based partitioning and decomposition of systems, are applied to get the smallest atom of a dynamic stochastic, the number of algorithms they generate could become countless. If parallel processing technologies, such as microservices, are used, the solution of a mathematical problem would be carried out by a swarm of algorithms that work autonomously and permanently to achieve the goal proposed by the decision maker. This algorithm swarm approach is currently used in artificial intelligence to manage swarms of robots, but the rules that robots follow are simple, logical and intuitive, and have no solid mathematical basis. An artificial brain can be visualized as a swarm of algorithms, cognitive robots, which have a communication structure based on a multi-level sparse matrix, and whose communication protocol is governed by mathematical laws aimed at obtaining team results. Creative intelligence is the fundamental basis for the development of mathematical theories that support mathematical models. For HY, this is an area of knowledge that is still unknown. To evolve from mental intelligence to mathematical intelligence, the human being requires another type of intelligence that allows him to perform the analyses to understand and discover the models that govern the universe that is written in the language of mathematics. Galileo Galilei, we will call this intelligence analytical creative intelligence. This intelligence can be considered as the highest level of human intelligence, since it is what allows to grow in the discovery of mathematical laws, and in general new knowledge, which is the engine of the scientific and technologic of humanity. In practice, very few humans have this ability and discipline. While humans in prehistoric times did not have access to mathematical intelligence, because they were creating it, today it is the engine of human knowledge, and ideally should be handled by all humans. Unfortunately, this is not the case. Therefore, its management must be part of the artificial intelligence that humanity is creating. The same thing happens with creative intelligence, the knowledge created by scientists, and the way to produce it is part of today's human intelligence. Enterprise-wide optimization systems. HYPOTHALAMUS, thanks to its peculiar vision of mathematical modeling, which is not based on computer programs, but on a relational database, which is used by a generative artificial intelligence that interprets the database and produces all the necessary computational code, can quickly implement what Professor Jeremy Shapiro called enterprise-wide optimization. In line with HYPOTHALAMUS' vision, enterprise-wide optimization systems are the evolution of traditional decision support systems, which have accumulated several mathematical models, many of them without following a standard, which ensures consistency across all models. These models run independently of each other, and are usually coordinated by a database, or multiple databases, that integrate the input-output. While each model can ensure optimality, this approach is not optimal, as there is no company-wide model. HYPOTHALAMUS first heard about AWO in the article Beyond Supply Chain Optimization to Enterprise Optimization, written by MIT professor Jeremy Shapiro, in which he states, AWO arises from the recognition that strategic supply chain planning needs to be integrated into broader business planning exercises, so that it serves to break down artificially created barriers to fact-based decision-making. In 2006, Jeremy Shapiro published the article Beyond Supply Chain Optimization to Enterprise Optimization, in which he stated, the recognition that strategic supply chain planning should be integrated into larger business planning exercises will serve to break down barriers to fact-based decision-making. Starting from SCM or supply chain management, focused on production, as a first step in standardized planning. Shapiro envisions what the S&OP, Sales and Operations Planning model, formally is, as the integration of sales and production planning. And finally, he establishes what is now IBP, Integrated Business Planning Model, which involves the financial planning as enterprise planning. That implies the incorporation of ALM models, assets and liabilities management, as part of supply chain planning. In the ERA of Industry 4.0, S&OP may be constructed based on 8 groups of solutions or systems: production, energy, maintenance, distribution, sourcing, human resources, financial, and sales and marketing. HYPOTHALAMUS view the systems as groups of equations that must be included in the S&OP mathematical problem depends on many factors. If the equations are defined in a database, the configuration of a problem is limited to selecting from the equation store, which are the ones that the modeler wants to consider in the model. Visually, it is easy to see the evolution of the traditional S&OP concept to a modern IBP, that covers, virtually, all the operational functions of an industrial organization. This leads to 2 problems that must be solved from a computational point of view. If traditional approaches are used, a large number of programmers are required to generate all the necessary source code, and to coordinate all the models, and large computational power is necessary to solve the integrated problem. At least, there are 4 dimensions to the optimal synchronization of a supply chain: functional, spatial, hierarchical, and business. They correspond to different points of view of the same problem. Mathematically, they must all produce the same optimal solution. HYPOTHALAMUS has developed algorithms specialized in the simultaneous handling of different points of view, to speed up problem solving. Artificial brains, integration of artificial intelligence and mathematical programming, are the result of HYPOTHALAMUS research in disruptive mathematical modeling methodologies for Industry 4.0. And they are the basis of the computational architecture of the enterprise-wide optimization systems. For more information, those interested are invited to watch the video. Artificial brains, artificial intelligence and mathematical programming integration. The starting point of the business hypothalamus is Professor Shapiro's concept, enterprise optimization, which we can synthesize, in its simplest version, as the IBP process.
El modelo IBP puede mirarse desde 3 visiones diferentes. 3 modelos independientes, que se integran por medio de un proceso en el que la entrada de un modelo es la salida de otro. Un modelo monolítico que integra los 3 modelos, y que se corre periódicamente, y un hipotálamo artificial que actúa autónomamente, de forma distribuida, en tiempo real.
The artificial brain is the evolution of DSS under the Industry 4.0 revolution, that is conceptualized as a set of mathematical models that exchange autonomously information between them, working online, using distributed optimization. This is how the human brain faces reality, using multiple models of reality, acting permanently in parallel, to make decisions. Based on the models to be integrated, and considering the magnitude, and the association between them, it is considered that the hypothalamus of a refinery business should be made up of 5 subsystems. Oil refining and petrochemical. Refinery industrial services. Water treatment. Multimode transport, and financial and fiscal. Large-scale optimization and artificial brains. One of the fundamental ideas of the artificial brain is the atomization of the system, bottom-up approach, to integrate multiple mathematical models, using the framework of large-scale optimization methodologies, like multi-level Bender's theory, and Lagrangian relaxation. To visualize the difference between the information provided by a monolithic model and an atomized model, we can think of a medical examination based on a photograph, and one based on an X-ray. Photography does not allow us to understand what is happening inside the human body, X-ray does. That is an advantage that cannot be achieved with a monolithic vision, which only provides aggregated information. Atomization allows to understand how a system is assembled, and how information flows inside. Artificial brains are backed by the technological capacity of computing. It is traditional to associate mathematical modeling with large-scale computing, which today is linked to cloud computing, integrated by supercomputers of bits, and by the birth of quantum computers, and its marketing process. The current state involves the integration of edge computing and cloud computing to implement highly complex mathematical models. OptEx, Optimization Expert System. Making high-complexity large-scale mathematical models. OptEx, the expert system for optimization, is used as the way to develop and implement AWO solutions, in which multiple mathematical models converge, and can be connected via a disk or cache databases, to form a monolithic model of the enterprise. OptEx is the generative artificial intelligence produced by HYPOTHALAMUS, which manufactures optimization systems for the entire company. Created in 1991, OptEx is used by HYPOTHALAMUS in the implementation of AWO systems. OptEx may be the only computer tool capable of integrating hundreds, if not thousands, of mathematical models, running on a parallel and distributed computer system. For those interested in learning more about OptEx, HYPOTHALAMUS invites to watch the video OptEx, Optimization Expert System. OptEx, Optimization Expert Systems, is oriented to the decision-making artificial intelligence methodologies and technologies that make mathematical models as Lego models. OptEx was created in 1991. OptEx is a generative artificial intelligence focused on the design, implementation, startup, and maintenance of artificial brains, based on high-complexity mathematical models. The way the mathematical modeler communicates with OptEx is through a standardized database, a unique data model for all mathematical problems or subproblems. This method is called structured mathematical modeling. It also allows to perform high-level operations between models, such as joining or splitting them, and implementing multi-problem solutions, according to large-scale optimization technologies, or using multi-problem procedures, such as constructing optimal numerical functions. Making an enterprise-wide optimization system, integrating multiple large-scale models, using a computer programmer, is an impossible approach, because the programmer can only write a limited number of lines of good source code per period. Maintaining these models can be more complicated than making them, if there is more than one programmer involved in the process. Only a generative artificial intelligence can produce infinite lines of perfect source code in seconds. The structured mathematical modeling, supported by OptEx, is integrated as part of these concepts. The final user benefits from all these capabilities, since the algorithms to which he can have access are in accordance with the state-of-the-art of augmented artificial intelligence, mathematical programming plus artificial intelligence, that supports industrial hypothalamus, as the modern form of the decision support systems for Industry 4.0. The R+D project focuses on enabling professionals, who are not experts in mathematical modeling, to build highly complex mathematical models, using the mathematical models stored in an OpText expert system. To do this, GPT methodologies will be used, so that the development of a model can be carried out through a chat, and later through a conversation. OpText GPT will become a cloud platform, by incorporating public models into the database, which will ultimately turn OpText GPT into a service for companies and professionals who want to implement mathematical models on the fly. The new way of mathematics is directly related to the parallel thinking, and today it can be said that like paper-based math, sequential mathematics for single-processor computers will be in the short term a dead language. As in the human brain, in the future only parallel mathematical thinking will be practical. The new analytics is autonomous, parallel, and distributed. Not teaching young professionals the principles of parallel rationing, derived from the new mathematics, is a serious mistake. Each society that does so, will end up paying its consequences, which in simple words, will lead to poverty, and a growing scientific backwardness, an abyss, which generates two different worlds, that will not be compatible. Albert Einstein said, "Imagination is more important than knowledge, because knowledge is limited, but imagination encircles the world."